Meeting is being recorded.
Okay, this meeting is being recorded, just to say to everyone. So I hope that all of you are safe at home and that this will bring like a bit of fresh air in this teleworking routine of these days. The focus of my PhD research is interpretability of machine learning systems for medical imaging. And my talk today will cover machine learning interpretability with some of an explorative approach. So this research field has been growing very quickly, and it could be tricky at first to have a good orientation with all the techniques that were proposed. So I would like to give sort of an introductory analysis that will give us a bit more orientation. Great. So how many of you are familiar with machine learning interpretability? And if so, like, do you think you could give your definition of it? In the subject of my PhD topic, I was also asked this question, and my answer was, well, it depends. You'd be like, what? It depends. You don't even know what you're giving this talk about then? Well, okay, the reality is that people are many and they're actually different. There are many different areas of expertise. We all have a different jargon. We even express thoughts and ideas in different ways. For example, let's consider a forecast for bad weather expressed by the term of rising barometer. This would probably mean very little to this toddler down here. It might be better understood by a veteran hiker, and it's probably obvious to a climate expert. So now you maybe get a bit more of the idea of why I'm saying that it depends. It depends on people, on who's the receiver, and what's its area of expertise and the ontology. And even more, it depends on what is the purpose of the interpretation. So based on the interpretability scope, there could be different ways. I counted at least 4 ways to analyze the same task. So here we go with the scope of the interpretation. So there are different scopes, and some of these, most of them were analyzed by Lipton in the paper, The Mythos of Model Interpretability, that I recommend having a look at. In this diagram, I show some of them, and we will see during this talk that each of them can lead to different interpretability analysis. So in some cases, we might be looking for something called algorithmic transparency. That is a clear and understandable procedure that brings us from a starting point to an output. In other cases, we might be interested in just translating what is happening in our algorithm to a specific user, maybe the patient or the clinician, or even the technician using a diagnostic machine, for example. If we're focusing on decomposability instead, then we want to understand in depth the role of each component in our tool. And in other cases, we might just be interested in giving contrasting explanations, so clarifying why a certain decision was taken rather than another. And in this case, we're focusing on explainability. Now, all of these parts are partially overlapping and they're partially complementary. So probably our desired target for interpretability is somewhere at the intersection of all of them, and then we can navigate towards one specific area rather than another, depending on the scope of the interpretation. If we were to look at what interpretability has been defined like in research, we would find several different definitions. We would for sure appreciate this quote. Interpretability is defined as the ability to explain or to present in understandable terms to a human. And I'd like to point out that not all humans are familiar with machine learning. This strong idea of a connection between interpretability and the human receiver has been nicely popping out in research in the last years, like a well-shared concept among the community. Even if we go a bit like broader outside of our research and our world of machine learning and computer science, we would realize that interpretability is in fact a translation problem from one language to another. And this leads me finally to introduce a definition of machine learning interpretability as a human-centric translation problem. So here it is. We have our task, and we would like to translate from one space, that is the space of explanations in the model representation space, so maybe the input pixels or the representations of the network, to another space that is the way human reasons. So maybe visualizations or simple concepts, or even just a sentence and like in caption generation. Now, why do we need interpretability? Do we really need it? This has also been a source of quite some debate. Let's start with an example first. Let's take a very classic scenario of a CNN, the input image of a cat. You've probably seen it a million times. It's correct classification, that's great. Most of us would be like, yeah, it works great. We can go home. This happens all the time. The day after, we start having doubts, maybe like, does it really work? Does it? So we decided to play a bit nasty, and we input the network some work of amatorial photoshopping. Still a cat. So the question arises is like, why? Why is that a cat? What options do we have without interpretability? I mean, the only thing a black box can tell us is that's the way it is. Quite confident about it. So this is clearly a bit unfortunate. And I don't think any of you would like a family doctor using this tool. So apart from the rhetorical question and the examples, I think that there is a series of hard questions that arise when we analyze the model behavior. That is, and this is why the interpretability is useful, and it is to answer most of these questions. So why the model is working, why the model is not working, would the output have changed, for example, with a bit more photoshopping? If some of you have heard about adversarial examples, they would probably know that sometimes even changing just a few pixels would be enough to completely flip a deep learning decision. So these questions like lead us to having a need for explaining defending actions. So saying, okay, I did this rather than that because, and also gaining maybe a bit of trust and push her to develop better models. So yeah, we can conclude that interpretability is a desirable feature that we would like to have. Important is to specify where is it needed, because we don't need it in all of our pipelines for sure. We know that in some applications, interpretability may be an important prerequisite. So there are, for example, health application, aptake, robotic systems that interact directly with humans. So that could hurt them in case of failure. And even teleoperatic systems are an example of a model that should not fail, otherwise it would have tragic consequences. Another example is assisted driving. Like, you wouldn't really trust a deep learning model to drive a car if you don't know that it's safe. So this kind of high risk application demanding this kind of high risk applications, we need interpretability. And over the years, there were even more applicability fields arising, such as daily legal practices, social sciences, and even finance. All these applications come with a high cost for failure. Actually applying AI to these fields has become also a demanding field for accountability, transparency, fairness, trust, causality, and many others. Now, one motivation doesn't cover them all. We cannot say that this covers all the panorama. There are clearly some areas where interpretability is unnecessary. For example, interpretability can be neglected in case of strict privacy requirements, where sharing model weights could maybe damage the security of a system. We don't need interpretability in the case the model has been confirming its performance and robustness repeatedly over time, over experiments and in edge cases. So also, for example, in low-risk applications, interpretability is not needed because making a mistake is simply no big deal. Finally, there are cases where the problem has been studied thoroughly and we're already very good at it. So think about flying somewhere. You don't really need to know how the airplane is working bit by bit to have confidence that you will arrive at the destination. Obviously, this has been a subject of intense discussion. Not all researchers yet agree on whether interpretability is indispensable and where. The next question is, how do we achieve interpretability? How do we get there? And that's the challenge and the current trend. Interpretability has been a subject of more and more research, and this topic has been touched also by many different conferences with new workshops and project proposals arising. Our goal today is exactly the how. So we want to work around this question to get to have a clear understanding and to get to know what to apply and where. And this is how we're going to get there. This is our outline. We would first have a quick look at inherently interpretable models. Then we will see how to interpret convolutional neural networks, and we would look at it from two sides. That is why this talk is called Inside Out, Interpretability Inside Out. We would first open the black box and look at internal activations, channels, and fields. So we will look at the inside of the network. And then we will say, okay, we don't know anything actually about the internal state of the network, but we do know input-output correspondences. So what can we do with that? And finally, I'd like to introduce you to some of our freshers' work on using interpretability actively during model development. Actually, not only as computer scientists, but also as users. So with very little knowledge about deep learning, but a lot of knowledge about the real task. If you have questions, we're going to have some time at the end of the talk. Also, I will not cover some interpretability area regarding exploratory data analysis. So, for example, all the dimensionality reduction stuff, like principal components analysis, independent components analysis, and also the more recent UMAP. Okay, let's have a quick look at inherently interpretable models. The easiest way to start with is linear regression. We model the output as a weighted sum of each input feature, so we have a direct interpretation for it. We know, for instance, that for a linear increase in the feature values, we would see a proportional effect, so either a linear increase or a linear decrease in the final output. The downside of this is that, however, there is no interaction between the features, and that the linear assumption might be too strong to get acceptable performance in some cases. In other cases, we can generalize this linear regression model by introducing our prior assumptions on the data generation process. Say, for example, that we know that the data generation process follows a binomial distribution. So we can change from this linear regression to aggregation of models of individual features. And in this case, the interpretation comes directly from our assumptions. And if you wanted, you could go even farther with generalized additive models explained by Caruana et al. Just keep in mind that the more you try to generalize to complex data generation processes and adding feature interactions that are nonlinear, then less we can actually interpret about what is going on. So there is this kind of three-sided trade-off between model complexity, model performance, and interpretability to keep in mind. Another approach that is inherently interpretable is to automatically learn a decision tree or to learn a set of rules that can classify your data. In the case of decision trees, this means learning a structure that splits the data into categories at each node. So for example, in this car model classification task, we can first discriminate about the energy source. So is the car electric? If yes, and then if the autonomy is more than 350 kilometers, then it's for sure a Tesla. This way of classifying data comes already embedded with trackable and explainable decisions. We even have an idea of data interactions because we can see which nodes are interacting to get to the decision. The downside of this is that it's good mostly for categorical features, and it would give us a bit of bad time if we're trying to interpret this model for a regression task. And also some people have been arguing that only shallow decision trees are actually interpretable since the complexity of interpretation increases drastically with depth, and they become much more opaque if they're very deep. Now, similarly, decision rules are a set of rules that lead to categorical classes. So for example, if the person capacity is less than 2, and the price is really high, and it's not electric, and the company logo is a horse, then the car is a Ferrari. So this set of rules has already an intrinsic explanation for our decision. This method is also sparse because if there are rules that are not useful for our task, then this wouldn't be considered and we would be able to see it, which makes decision rules quite efficient. The problem is that, again, it's not good for regression. It's only good for categorical features. And similarly to the decision trees, complexity grows with the number of rules. All of this was just to give you an idea of what are inherently interpretable models and why some of them were criticized as not being completely interpretable. And why do we need to go beyond that, starting also just to look at test accuracy that has been overcome by the introduction of more complex models such as deep learning. Which leads me to the second part of this talk, where we analyze how to interpret more complex models. Before, I'd like to give you some terminology that we might find helpful as we go over with our overview. There are, for instance, local versus global explanations and model-specific versus post-hoc approaches. These terms are useful to cluster the interpretability methods in smaller classes that highlight or measure the differences among them so that given a problem, it's easy to find what set of techniques may be the most appropriate. Now, local explanation is true only for a specific instance. So let's say we have an input image. We would like to have an explanation only for the corresponding output. So then in that case, we'd be looking for that local explanation. If these explanations are true instead for a set of input, for example, for an entire class, then we would be talking about global explanations. A model-specific approach is a way of building an interpretability analysis already like built in a specific model, or that anyway applies only to a particular model. For example, some network giving also attention maps is a sort of model-specific interpretation. Post-hoc approaches are a bit broader than this. They are applicable to any model without the need of retraining the learned parameters. And this is a great starting point for an interpretability analysis because it does not require to build a specific model for it. And this is also why we will cover mostly post-hoc methods in this talk, because we can take what we have already done in our applications. We could take the models we have already, and we could interpret that as a start. So, okay, we will start by opening the Pandora box and looking inside. So we will first see how we can interpret the network by looking at its internal component activation, so layer, channel, neuron activations. And these techniques here, again, can be clustered according to their approach. We will first have a look at database search methods that inspect the database by finding images that maximally activate, for example, a layer or maximally activate a neuron. Then we will look at image generation approaches, so visualization techniques. And finally, we will have a look at a different technique that has more of a geometric approach to analyze internal activations. We will then move from the inside to interpreting deep learning from looking at input-output correspondences. And examples of these techniques are surrogate models, and then widely used attribution to features, and the more recent approach of attribution to concepts. And so here there's just a sum up of the techniques in each cluster. We will talk about most of them, maybe some more in details than others. Now, this is obviously not exhaustive. There are many more techniques in this field, and there are several specializations for specific applications. But in any case, this should give us a good overview of the main ideas that have been evolving over the years. Okay, let's start. The first thing we're looking through is database search. The idea is really simple. We address a question that is, what examples explain the data? For example, what examples maximally activate neuron for neuron response? So this is, again, a method that requires looking at the internal state of the network. It is post-hoc. There is no need for retraining the parameters. And it gives us a global understanding, in most cases, of either the data or the model. Generally, when we talk about database search, we're looking at instances in our data that are representative of all of the data, all data. And these instances are called prototypes. A recent technique, a method called maximum mean discrepancy, however, point out that examples are not enough to understand our data, and that we also need to look at those instances that are underrepresented in our data collection, and these are called criticism. So in those words, what the maximum mean discrepancy procedure proposed was to find first prototypes that can model closely the data distribution, and then find criticism by looking at where there is a maximum discrepancy between the data and the selected prototypes. And these techniques can give very useful insights on how to build a machine learning model that takes into account all the data differences. And it could clarify also unexpected decisions made, for example, by a black box algorithm. Another way to search the database is to look for instances that are critical to the learning process. For example, by looking at those instances that, if removed from the training set, would strongly change the learned model. And these are called influential instances. Now, some of you may already be shaking their heads thinking, no way we can retrain every time we delete one instance from the training set. That's a really good point if you're thinking this. And we can approximate actually this. We're not going to do this, but we can approximate it with influence function. So this paper was presented at ICML 2017. is suggesting that the change in the learned parameters of a network can be computed, can be estimated, rather than having to retrain every time. And so we would obtain new parameters as if we were deleting the instance, and we would be able to measure the impact of deleting one instance. This method is also postdoc, and it gives a global understanding of what would happen if a specific instance did not exist in the training set. So it gives us more or less an idea of how the model is making the learning. In this picture, for example, there is this image of a dog on the top right was useful to classify also the class of a fish. So it's telling you more or less, okay, look, in a deep neural network, you don't only look at fish, you don't only look at the color in the image, but you also look at more complex concepts. Okay, a fish is not a dog. Let's now move to image generation and visualization techniques. In this case, we would like to have a visual response that tells us what is a neuron, a channel, or a layer looking for during training. One approach was deconvolution, and this was proposed really early. The basic idea is to interpret the neuron or the channel by reconstructing the activation zone of influence in the input space. This is done by inverting several times, so the pooling, the ReLU, and the convolutional operations that the image has gone through once inputted in the network. And at the end of this, we can obtain a reconstruction of the image that we can see in this very good video that I took from a lecture online by Stanford that is on YouTube. It's for free, and I strongly recommend all of those that might be interested have a look at. So we can obtain a reconstruction like this, where we know that the neuron activated because it responded to the dog ears. Okay, so this technique is postdoc, doesn't need retraining, and it is local because it gives us an interpretation for a specific input. Another different approach is activation maximization that aims at generating an image where you're solving an optimization problem. So it means finding an input that maximizes the response of a neuron, a channel, or a layer. And this is done by starting from a random noise input and then updating its pixels iteratively with gradient ascent so that the gradient response of the neuron is maximized. The backbone of this technique was proposed already very early in 2009 and was then refined over the years, arriving to obtain almost natural-looking images, like those obtained by the Lucid toolbox by Ola and other people at Google. And this is again a postdoc approach for global explanations. Let's look now at network dissection by the group of Toralba in Boston. This technique is also global for postdoc explanations, and it tells us a bit the role of individual components inside the network. We still open the black box. In this research, they started from a database of roughly 1,000 images with ground truth segmentations of concepts such as object color, texture, material, object type, and scene. So for one input image, like this one on the left, we have a set of binary masks of the segmentations of all the concepts present in the image. So I don't know, the blue, the fabric, the door, there is a person, and the car segmentation that is the biggest portion in the image. Now from the activation maps of the network, we can compare the threshold activation of individual units with the ground truth segmentations. So we pass the input image, we take the activation map, and we threshold the activation of each individual unit. And we compare this thresholding operation with the ground truth segmentations by evaluating, for example, the intersection of a union. So the key point to do this here is the upsampling operation that brings the convolution, the feature map to the target size. And the results that we obtain give us an understanding on the learning dynamics inside the network, showing that early training, for example, focuses on finding the concepts first, and then these concepts are refined later during training. So I learned better and better over training. Last of the techniques that look inside the network that we will look at today is singular vector canonical correlation analysis. This method poses a different question, as like, can we compress what a layer has learned by looking at all training examples? So again, a global post-hoc method, and here's the idea. We select a layer of interest that is in evidence in orange in my picture here, and we store its responses to all the inputs in the training data set. In the paper, they used ImageNet, so they stored all the responses of the layer to the images in ImageNet. Now, all of these activations can be piled up to form a huge tensor that is here at the bottom, which is then analyzed by singular vector decomposition and canonical correlation analysis. So this technique applies quite to different thinking compared to the others, and it gives insights on the learning dynamics, and it allows to compare different layers of different architectures. So for example, we could compare a layer of Inception v3 to a layer in ResNet and see if they learn similar representations. Great. We had now a look at all the methods that were opening the black box, and we can start looking at input-output correspondences. The first thing is surrogate models. So a surrogate model is an inherently interpretable model that is trained to learn the black box prediction on the training data set. So we just replace the model that we cannot understand with something that we can understand, and we learn how to approximate this curve. For example, here, this linear surrogate is trying to approximate the complex decision function of a neural network. Now, the good point of this approach is that it's very flexible. So we could have different interpretable models being used. In some cases, for example, a decision tree might be more convenient, and it could be used rather than a linear regression, or maybe a set of decision rules could be used too. So they could be switched, and they could give different interpretations. The downside of that, though, is that in case of linear surrogates, for example, a linear sample may be too strong in some cases. So it's very approximate. In case of decision trees and rule sets also, they would have to be kept quite shallow to have a clear interpretation. Again, this is a global post-hoc approach, and it can be refined even farther by looking locally. So we could, like local interpretable model-agnostic explanations, for example, is a method to obtain local post-hoc explanations by local surrogates. So rather than learning a replacement that would approximate all the black box predictions altogether, we select a neighborhood of inputs around one input of interest. And this is used to learn a local linear surrogate. So for example, we can use this technique to explain the contribution of sets of input pixels in the decision given for a given class for a given input. So here we have this image of this dog playing the guitar, and we could select the class Labrador, and we could see what pixels are given the decision. So what set of subpixels. This method is quite universal and flexible, being post-hoc, but it comes with a few problems. For example, it's not really clear what the optimal size of the locality should be. We could choose a different locality. We don't know what would be best. Moreover, the sampling of the instances in the neighborhood is also not too robust, because different samplings could lead to different explanations. For example, here, a different sampling of the data points gives me another linear surrogate, so it's totally different explanation. As another technique, Shap values were proposed as a unifying additive framework for 4 or 6 different interpretability techniques, including LIME, so the last one that we just saw. So the idea is that each feature contribution can be estimated by looking at the change in the expected model prediction when we condition on that feature, which is great for categorical features, but gives quite some limited abstraction in images, because the results remind a bit of saliency maps. So they just highlight a few pixels, but it's not really clear why. Which leads me to the second bunch of techniques that considered attribution techniques. Now, in attribution to features, we're looking for a vector of scores that tells us the contribution of each input pixel to the output. This, for example, can be computed by saying, okay, how would the output change if we change this pixel value? And this is more or less the definition of saliency maps. So it's a derivative operation of the output over the input. Which pixels in the image need to be changed the least to affect the output the most. And this baseline idea was then refined and improved by several other works, such as integrated gradients and guided graph propagation, and many others. Now, one main criticism to this was that saliency was shown to be quite unstable and unreliable in edge cases. So, for example, in networks with randomized weights, or even when compared to a random attribution map. And if you want to dig in a little bit more, you can have a look at the paper Remove and Reframe that evaluates specifically all of these saliency techniques. We can have now a look at the class activation mapping. It's quite a popular technique that was used to have that was used at the beginning to show that CNNs have great localization properties. So this technique gives, in fact, an idea of where the network is looking in the image to take the decision. We can do this by aggregating the feature maps of an internal layer as a weighted sum operation, where the weights are given by a global average pooling layer before the final softmax. Now, some networks like Inception have already a global average pooling before softmax, and other networks may not have it, like AlexNet, for example. So this can be added, this global average pooling operation can be added as a last layer, and it is very fast to train because it's just one layer. And this technique was very successful because of its transparency and directness, giving a clear idea of where the network is looking at. One issue with it is that it seems to fail to give focused heat maps when there are multiple instances of the same object. For example, we had some difficulties in our histopathology application because we have multiple nuclei in the input image, and we were failing to get very sharp heat maps highlighting maybe the nuclei precisely. Lots of work anyway had been done on top of these, such as RadCam and even GraphCam++ that partially addresses this limitation that I just mentioned. Okay, we can now move to attribution to concepts. And the bottom idea here is that if concepts can define object categories like animals, people, cars, etc., why don't we directly estimate the relevance in the classification? The work on concept activation vectors pioneered this question. Let's say that we have a zebra, for example, and we would like to estimate the relevance of stripe texture in the classification of the CNN. One thing we can do is we can collect a batch of examples of the stripe texture concept. We pass them, we feed them into the CNN, and we take the responses of a given layer. So again, the orange layer inside the network here. And these responses essentially are a set of feature maps, and we can flatten them into a vector that can be used to solve a linear classification problem where we classify the representation of inputs representing texture from inputs representing just random images. Here, for example, we have this image. We have an example of all striped texture in the bottom left that is classified versus any random image. And this, we can take the orthogonal vector to the classification direction as representative of the striped texture concept. And this vector is called concept activation vector. The last step is to determine the saliency of this concept, which can be done by generalizing the definition of saliency that we saw before as a derivative of the output over the concept vector, which means computing a directional derivative. This value is telling us how much the output for a given image would change if a slight change happened in the representation of the concept. So this method is a concept-based saliency for a given image. And it's a poster method for local explanations because we could have an image and a concept and no measure of saliency for the given image and the given concept. However, the authors proposed also a Tikov score that allows to accumulate all the individual saliencies for individual inputs into a global score that is indicative of the relevance of a concept to the classification for a whole class, for example. So So this method gives both local and global interpretations. And this research was a great work. It had a lot of positive feedback and several different applications. One limitation that caught our attention was, however, that it's defined only for concepts that have a binary representation. So the concept is either present or absent. And this works very well on some kind of images, like natural images. But in other applications, such as medicine, for example, many concepts have categorical or even continuous expression. I don't know, tumor extension, for example. This motivated our research on regression concept vectors that can be expressed, so where concepts can be expressed in continuous forms, so like measures that we can directly compute on the input images. And I will show you this in detail in the next slide. We start from a set of input images, of which we have manual annotations of objects of interest, or from which we can automatically segment instances if needed. Now, from this segmentation, we can measure a set of feature of interest, like, I don't know, first order statistics, for example, of pixel intensities, second order statistics, so texture descriptors, also measures of shape and size. Now, similarly to CAVs, we pass all of these images in the network, and we extract the internal activations, and we store these internal activations, but we aggregate them with a pooling operation, like global average pooling. These activations are then used to learn a vector, also in this case, that is found by solving a linear regression problem rather than a binary classification problem. So in this example here, we are trying to learn object size, and the regression is learned in the hidden space of the network, actually in the space of the pooled activations. And each point here in this figure is representing an input image, where the size of the circle is representing the segmentation size. And so our linear regression will learn the direction of increasing values of a concept, in this case, the concept of size. The final step is, again, evaluating the saliences of the concept vector as a directional derivative. You have already seen this. And so similarly to TCAV, our approach is also both local and global, and is a postdoc. And we applied this technique to several different fields, and we also won a Best Paper award for that. Now, our primary focus is health, so we applied it to the classification of breast cancer histopathology tissue. We started from the modeling of visual concepts used by clinicians to manually take decisions to something that we could automatically extract from the images. For instance, we took the Nottingham grading system that is very popular in breast histopathology and is used to detect tumor tissue, and it takes into account tissue appearance, particularly if there are variations, for example, in the nuclei appearances. These variations are generally depicted as nuclei being larger and less homogeneous than normal with weird irregular texture. So we found this progression from clinical concepts to something that can be a measurable attribute, that can be the size of the region or the texture and the nuclei contours. Coming up with visual descriptors that are measurable from the pixels, such as area, texture, contrast, etc. Now, our second step in the analysis was to attribute these concepts to the decision taken by the convolutional network. And we did this for the tumor and the non-tumor classes. So we looked at novel explanation of our network. Interestingly enough, we found that the network was sort of in line with the guidelines. So for instance, the relevance of the concepts that we analyzed matched with our expectations from the grading guidelines. Another application in health for this technique was in retinopathy of prematurity. So the Martinez Center and the Case Eyes Institute had a network to classify the presence of plus disease in preborn babies. In very shallow words, in these babies, there is an abnormal growth of the retinal blood vessels. And if not promptly treated, this could degenerate and cause the total detachment of the retina, so blindness. Now, the ophthalmologists at the Case Eye were interested in the relevance of some handcrafted features that were used in literature before their deep learning model. And so we could estimate this importance from both a local and a global perspective in the deep learning model that they had trained. RCVs were also then improved and applied lately on a radiomics application by another group, another research group. And since our tool is quite simple and straightforward to apply, we also played around with it a bit more, and we used to interpret the relevance of digits, shape, for example, and orientation in computer vision, so with a data set of handwritten digits. And we also used to measure, for example, the relevance of scale at different layers in an inception and in ResNet networks. For example, we took here images of albatrosses and approximative measurements of their scale in the image, and we used this to learn a regression model that would predict their scale inside the network. And by evaluating the predictive performance of the regression, we could convey that information about scale is indeed present through all the network layers, and that invariance on ImageNet is only achieved before softmax. Another fun application was investigating learning processes of concepts, especially in case of corrupted label correspondences. So if we train the model with wrong labels for some inputs. This is representative of some real applications that may only have weak labels or, for example, noisy data. And we learn measures of color and texture, like the blueness of an image, that was expressed from a scale from 0 to 1. And now the representative power of a network like Inception makes the network memorize the noise. So it would overfit the training data, would still have great performance, even in case of wrong labels. And one thing that we saw is that actually unwanted memorization can be spotted by modeling the loss. And for instance, here in this plot, the convergence on the noisy input is the orange line, and it's much lower. And that is the memorization part. But even more, we noticed that some of our simple concepts of color and texture were used to memorize the correspondences. Great, so thank you for staying with me up to this point. Our goal was to get to know what to apply and where, so how to gain a clear understanding about applying machine learning. And I hope that this walkthrough was useful for most of you to gain a clear understanding and a better orientation on the landscape of possible techniques. I'd like to remind you that it is always important to start by understanding what do we need the most in our analysis. We need to maybe understand each component and their interaction, or each of them individually. Well, maybe in that case, we could use gradient descent. If we want to make comparisons across networks instead, then we might look more into geometric approaches. If we want to obtain quickly visual explanations on simple inputs, then there are class activation maps and layer-wise relevance propagation that could be worth looking into. We have skipped the last one, but it's very well documented already. If we want to have a global understanding, we may first want to have a look at local surrogate models or surrogate models. If we're looking for user-friendly explanations, so maybe by measuring image attributes or by having a data set of conceptual examples, we may look at RCVs and CATs. What else? Can we go beyond the interpretation? Yeah, and that's exciting. I can show you now some of our current and still unpublished research. We're using interpretability to obtain better control in model development. Let's go back to our example of the beginning. So yes, this is still a cat. And we know that this classification is happening because network is focusing on the pointy ears and the mustache of the cat. Okay, so we know what's happening. But wait, cats don't have penguin legs. So can we work on this feedback loop here to develop some robustness to adversarial, for example? Can we enforce the network to notice the penguin legs and react to them? This is something that we're currently looking into, and it is very exciting because if so, then it could mean that we could gather application experts in a room and use them to instruct networks and introduce a better control on concepts that are relevant and concepts that are not relevant to a task. We could, for instance, start from our interpretability analysis, some prior knowledge, and the feedback of end users, to model additional targets that our deep learning model should meet, like, for example, sensitivity or the opposite insensitivity to a certain concept. And that's how we thought of doing so. So, for example, modeling the prediction of the side features as a multitask learning problem, and the removal of undesired features as an adversarial learning problem. And I'd like to say more about it, hopefully in the coming months, we will have some feedback about it. So here there are some takeaways from today for you. I hope I managed to convince all of you that machine learning interpretability should be seen as a human-centric task to really be tailored on each of our needs. And like, I don't know, as a takeaway coffee, I would probably prefer a cappuccino with soya milk, and maybe others would take and be happy with a dark black coffee. So similarly, one type of interpretability analysis may be more useful and understandable to some users than to others, depending on their background and their needs. And whenever you may be in doubt about when to start from, I suggest you to have a look at the slide 121 in this talk, because you can use it a bit to navigate around and see what would be the best choice. Now, there is also here a list of growing conferences, workshops, and interesting people in the field. And I think it is definitely worth following this if you want to get involved with machine learning interpretability. Again, this is absolutely not exhaustive, as these are only like main conferences on computer vision applications, and there are tons of more specific applications on different approaches and different methods. Thank you very much for following me in this talk. I hope you enjoyed it. The last picture here is just a summary of our vision for machine learning interpretability in healthcare. If you want to connect, please do so. I'm quite active on different social media, email, whatever. And if you have questions now, I'll also be happy to answer, or if they come up later, and you can back to me.
Okay, so anybody has questions? If not, then I have a small one.
Okay.
So you were talking about robustness against adversarial examples as basically, let's say, modeling target, right?
Yeah.
So have you tested how your method on concept vectors, concept activation, and regression concepts work under adversarial examples?
No, okay, no, this is something that we were thinking of doing. We haven't done it yet because there is a lot of work on adversarial examples. I mean, you could always create an adversarial example, an example that is adversarial to your specific network, and that could also fail and fool your interpretability method. But, we haven't done it, but I have seen some work that took a specific interpretability method and said, look, now I'm gonna fool it, and it's not gonna notice this adversarial example. That's the reason why we were hesitating a bit, thinking about how to do it. But yeah, it's definitely interesting to have a look at too. Yeah.
Thanks.
I have two questions for you. So the first question is regarding the global activation map that you showed for histopathology detection, interpreting tumor images.
This one, you mean?
Way before that. The easiest way to, like, before even the heat map prediction for tumor regions that you had. Let's say there are several nuclei.
This one. Yeah, this one.
Yes.
Yeah.
Yes. So in this case, so which were the classes that you included? Were they just tumor versus non-tumor?
Yes. Yes. It's a binary classification ResNet. It was 121 layers, and we're classifying tumor from non-tumor patches.
Okay, so as I can see in this particular diagram, there are several cells that are cancer. So since they are very heavily clustered, so maybe few of the cancerous cells are representative enough for the entire region. You may not need all the nuclei to be interpretable enough to say what type of patch it is, correct?
I agree. Yeah.
And whereas in the binary case, like this type of cells will not be available at all. So maybe they're easier that, so just then what is your take on saying that why this, like the issue that you mentioned for this paper? So little focus on multiple instances. Maybe few instances are good enough to represent because your classifications are easier. The task is easier.
Yes, so I agree with you. This was also, I mean, this is also our hypothesis, so that the network needs to find, I mean, to know if there's tumor or not, you need to find one, two tumor-looking cells. You don't need to see all of them or to spot all of them. It would be already enough to have a detection of some. But you see that it's not complete because you don't know if it's focusing on them because these are enough, or if it's focusing on them for other reasons. This was the first point. Second point is that not all of the visualizations were looking like this. So in some cases, you might have tumor cells that are close to tumor cells, and you will still have a class activation map on those. And you could have an activation, so the heat map read on those, but it would be not very well defined. So it's not very well defined around the borders of the nucleus. It's a bit in between the two. And the problem with this is that it's not clear if it's focusing on the tumor's nuclei, if it is focusing on both of them because it's noticing the differences, or if this is just a problem of how CAM was implemented. Because if you look at the, for example, the paper that I suggest to look at is GradCam++. So they took a GradCam, and they even improved it better to have to introduce pixel level weights. So the weights aren't anymore on the entire feature map, but they are on each pixel, and this gives you a tiny bit more of precision. And actually, this image here that I'm showing was computed with GradCam++. So we arrived to this level of definition by using this improved technique, but you see that even by getting there, it's not yet as good as I wish it was, because I would really like to have. Now, there's also been more work on this. So for example, I talked to a guy that worked on the size of the effective receptive field of the network. Because if you take a very deep network, the effective field would be very, very large at the last layer. And this might go against the fact of having multiple small instances of the same object in the image. So these guys worked on reducing the effective field already in the network construction to have more precise class activation maps. But then again, the problem is this really interpreting because this is happening, or is it interpreting in this way because we forced it to be in that way so that we're happy? It's a bit clear.
Yes. Okay, great. And I have one more question on your iMimic paper. Yeah, the next one where you showed the application on histopathology. The next slide. Yes. So for the nuclear pleomorphism, you are focusing at individual nuclear level, right? So how did you select these attributes, let's say area, contrast, and all this? Were the intuitively selected for this task?
No, it wasn't. Well, okay, so we started by reading the grading guidelines, and then we tried to model what was explained in the text, what was described in the text by some features that we could easily extract from the images. Now, we used the segmentation of the nuclei, and we for each nuclei instance, we computed, for example, the area as a number of pixels. And then what we took was, we looked at both average and max area. So we looked at different ways of aggregating the information about the multiple instances. And we started with simple average because we saw that it was working the best. I mean, it was working much better than taking just the max. So
okay. So how do you see applying this technique to a tumor patch? Because it's focusing at the nuclear level. So obviously the image that How do you think this system can be leveraged to maybe address those kind of patches or so?
Honestly, like it's been working really well now. I need to understand a bit better the question maybe because the concept it's still learned through a regression, and we need only a few samples. So we took a few samples of tumor patches and a few samples of non-tumor patches, and we computed for each of them. I think it was 30 or 50 images. We also tried with 100 and 300, but we saw that the performance of the regression was, the regression was the same. So, and then for each of these images, we computed the average area of the nuclei inside the images, and we used this to compute the regression. And once you have that, you have the vector. So then you just need to compute the sensitivity for all the other inputs. Yeah.
Okay. Okay. Yeah. Great. I understood. Yeah. I have to go through your paper then. Thanks. Thanks a lot.
Okay, cool. Not all. Any other questions?
Do you have any idea if these insights that you gained could also be used in, for instance, removing bias? When we're thinking of face recognition, a big subject there is racial or ethnic bias, right? Any ideas in that direction?
Yes. This is exciting. It's our latest work. It's something that the idea is around here. So we know that in the data collection process that we have, there is some bias. Now, in face recognition, honestly, I'm not an expert in the field. I should do some reading, but I can tell you, for example, an example of predicting pneumonia in cases with and without asthma. So there was this model that was trained, and it was giving a higher risk of mortality to people that had pneumonia at the same time with asthma. This was wrong. Sorry, a lower risk of mortality. And the problem with this is that there was a bias in the training data, where all the patients with asthma were given a better treatment, so they had lower risk of dying because of the better treatment, not for sure because of this kind of correlation between the two features. So in this case, we know that if there is some bias in the training data and we can input feedback in the training of a network, we could input feedback in such a way that we would remove this bias. This is what we're trying to do. Another example could be removing background or lighting conditions. Like if I think of image recognition, we could remove maybe the information about the exposure of the image.
Okay, great. Thank you.
Yeah, so again, I'll leave here the email and contact. And if you have any other questions, if you're looking for the papers, they're almost all on Google Scholar with the direct link. They're also on ResearchGate, and some of them are, there is an entire list on the publication page of the HEVs. So if you do publication.hevs.ch and you search for mining, you will find all of my publications, even though I think Scholar is